Hi guys, just wanted to do a little walkthrough of Lab 8, what's required on Lab 8, and also at the same time I think it'll serve as a good tutorial for Logisim because I think a lot of us are seeing this for the first time, and we're going to use this pretty heavily for the rest of the semester because we're not going to be able to do a lot of our stuff online. Sorry, in class with the actual hardware. Um, so the goal of today is to make a machine. This is Lab 8, by the way. Make a machine that looks like Petzold's Harvard machine from page 215 of your text. And if you left the book in your room when the zombies came, that's totally fine. Just go to Sakai, and you'll see on the resources, in the resources tab, there's a link for Petzold's code text. So you can just open that, and that'll show you this. It's actually on page 205 of the PDF version instead of page 215 of the physical text if you have the physical text. So we're going to make this. It's the simplest 8-bit adder, really. 8-bit, it can add and subtract, it can store. So it's the first automated machine. It can also almost be called a computer, except we don't currently have the ability for it to make decisions. That's coming soon. Okay, so you can also get the lab from the resources tab if you go under labs. This is Lab 8 online. Okay, I need to add Lab 8 online. Apparently it's not there yet, but it'll be there very soon. It looks like this. And it basically goes through what Petzold does in chapter 17. And the first thing it does is we kind of arbitrarily define these opcodes for the different operations we want to do: load, store, add, subtract, and halt. So we've given them these binary codes. This is the hexadecimal equivalent of these binary codes. So the first thing we need to do is come up with a decoder ring that tells the machine that we're making what we want to do. And this is a reminder of how and NOR gates work. ANDs are only on if all of the inputs are high, and NORs are only on if all the inputs are low. So we can use that to make a decoder like this. It's a little bit like this. We have our opcode. In this case, this is the opcode is first nibble is a 1 and the next nibble is a 0, so the hexadecimal equivalent of that would be 10, and I've just put a probe there to show that. And the code, the code 10 corresponds to the load operation. So this is for a load operation, and you can see that we've lit the light that corresponds to the load operation. So our decoder is working for this. So our goal is going to be to fill in the rest of these, and actually we need to add one more for subtract. And you're like, what is this thing and what is this? So I want to show you. So when you open Logisim, you'll see a screen like this with the Explorer pane. And the first thing we want to do is we want to add another circuit, because we're going to make a decoder, and we're going to end up adding a bunch of these sub-circuits together into a big circuit that's going to make our machine. So it's a really good way to organize our stuff. So under Project, click Add Circuit, and let's call this Instruction Decoder. So I need to make these things. So the first is an input. So we'll make an input that faces east and has 8 data bits instead of 1. And we don't want 3 state. We just want it either on or off. And the label, we'll call it opcode in. And let's put that down. Okay. Yeah. It didn't like that I put it off the screen. So you notice how it starts in 3 states, which is not good. So I want to make them all either 0s or 1s. It should be no. Alright, and then next thing we have this gadget, which is a splitter, and you'll find that under wiring. So you can click on splitter, we'll put it there. And anything coming out of this, if I were to draw a line like this, we'll get this incompatible widths error. It's because we have 8 bits coming out of this input box. So this line has 8 bits of information on it, but we're only accepting 2. So to fix that, we need to make sure that our input is 8 bits, and our fan out needs to be 8 bits, because we want to go to 8 different inputs for each of these NORs. Okay, and then next thing I want to add is some NOR, so I go under gates and I have a NOR gate. I want to face this south. I want 8 inputs. And what else can we do? Yeah, let's make it, nah, that's fine. Medium's fine. Don't need a label. Okay, I think we're good. So we'll do one here. We need 5 of these, I guess. So need a little more room. Actually, do I need 5? Nah, I only need 4 of these, and we're going to use an AND for the halt. It's just easier. I can, well, actually, I'll do it both ways. I'll show you. So we have 5. This is my output, so we'll face that north. And I want to give it a label of load, and want my label to be south. Oops. Alright, we're getting all these errors because we don't have any input, so it doesn't know what to make of it. So I want to route these to each of these input gates. And I know that the opcode for halt, which is what I'm going to rename this last gate, is 11111, so FF in hexadecimal. So if I'm using an AND gate, these would all be not inverted. And I would get a 1 signal on my load, but I'm using a NOR gate, which means I would have to invert all of these inputs to get the same result. So I can do that by selecting the gate and then just saying yes for all these inputs. Now you see that I get my load signal when I have a 1111. And perhaps you'll find it useful, I find it useful, to use the probe that tells me what is the hexadecimal equivalent of what I'm writing here. You select the radix tells you if you want it in base 10 or base 16, and you can put a label if you would like to add a label. Alright, so let's look at the load. The opcode for load is 10. That means this pin needs to be inverted. How did I know that? Well, let's look at we look at 10 in binary, and everything is 0 except for the 4th bit over. So that means this guy, the 4th from the left, has to be inverted. And so, you know, now when I make all these connections, are we having fun yet? And I use the poke tool to set this to 10. So that's 1. That's 0, 10. Now I get the load light lit. So it's correctly working for an opcode of 10 load. Alright, now the next thing on our table is store. So I want this to be store. And store is a 1-1. So here's a kind of a way to cheat, if you will. I can see that this line and this line need to be inverted for my NOR gate to be high. So when I make these connections, I want to make sure that the 8th gate, here the 4th gate and the 8th gate are inverted. And now when I connect these up, I see that I get the store when the opcode is 1, 1, 1. So hopefully that gives you an idea of what we need to do for the decoder. There's one more thing I'd like to show you, which is how to give it a symbol. Here, I want to stretch this out a little bit because we're going to need this room, and I'm going to give it a label, which is going to be kind of big, and it might help us to stretch these out a little. There's actually going to be a few more. So we're going to have, did we do subtract? Check. Load, store, add, and subtract. Okay, yeah, that's it for now. We're going to add a few more later. Okay, so I'm just modifying the appearance of my circuit. This little green line tells me what direction the thing is going to be facing. I don't really need that. That's usually for a clock. This tells me where the input is. Let's say I want this a little bit thicker. Alright, that looks kind of symmetrical, I guess. Yeah, okay. And then you can hover over, you can click on outputs, and it'll show you what it corresponds to. I don't know, that was kind of quick, but do you see this corresponds to the second input, which is store. This is the third, which is add, and so on. And if you have your outputs labeled, you'll actually see that when you do this next thing. So if you go to main, you have to double click main until you see a little magnifying glass there. And now let's say we want to add our instruction decoder to this big circuit. Well, I just put that in there. I can give it a label. Oh, in fact, let's do a shared label. And I want that shared label to face north. Perfect. Now when I hover over it, it tells me what it is. This is opcode in. That's load, store, add, subtract. Oops, that should be halt. So we need to fix that. Okay, I think we've done. That's our decoder. So the next thing we need to look at is our selectable inverter, and I think I've already talked about how you can use a exclusive OR gate as a selectable inverter. So let's add a new circuit. I'm going to have 2 of those, and this is, I'm just looking at the lab, right? So I'm copying these inputs from the lab. This is another 8 opcode in. This is I need 8 data bits out, and then I need an exclusive OR gate. Let's face that south. Make it narrow, and 2 inputs. Alright, and then our fan out's going to be 8 data bits for the input, and same with this. Want that facing east. Alright. Just trying to think of the order. Yeah, I guess I'll just do this. So this is going to correspond to the 7th bit, or least significant bit. Actually, I think it's the other way around. Most significant bit. Okay, now I need an inverter input, so let's put this over here someplace. That's going to be 1 It's either on, it's either telling it to invert or not, and I want that to face west. And this label is invert. Let's put that to the east. I don't want 3 states. Okay. Why are you... Alright, I unselected my 3 states, so I don't have... The X means it's floating, it's neither high nor low. Alright, now if I select 0 for my invert signal, then I expect that whatever is going into this bit... Oops. Yeah, I did have that backwards. Okay, so 7 is the most significant bit, and 0 is the least significant bit. Okay, so for my most significant bit, if I have that high, and I don't invert it, then the output is going to be high. But if I invert it, now the output is low. So this is the way we make a selectable inverter. I just need to do this a bunch of times, because I'm going to do this for every bit in my signal. Okay, 7, so this goes to 6, 5, and so on. Okay, well, I think you can see for the 3 bits that I've done, I'm successfully inverting my signals. Here I have 1, 0, 0, and no, I can't see that I'm doing it. There we go. Yeah, now I have 1, 0, 0. It should be giving me 0, 0, sorry, 0, 1, 1 when I invert it, and 1, 0, 0 when I don't invert it. So please just finish this out, and then you might want to modify the circuit for your selectable inverter. I think the way I did mine was I made a triangle, because it's basically like a big NOT gate. I guess that works. And that looks like my input, so I'll put that right there. This looks like my output. And my facing, and this thing will tell me if I want to invert or not. Yeah, that looks good. So now when I go back to my main, if I want to add my selectable inverter, I just click on that once, and hover over it, I see that I've didn't label that output. This should be my inversion output. So let me go back and label this. Should be data out. Should be data in. Alright, let's see what's next. I've got, oh, right. Okay, well, the way we implement the halt signal is we're going to have a clock with, this is good because I get to show you something. The clock, here's the clock signal. If I want to turn off the clock when I get a halt signal, I can use tunnels. So this is our halt comes out here. If I use this tunnel, this is a way to wire things together without running them all over the board. So whatever, the easiest way to do this is to copy it. Wherever you have another tunnel that's got the same name, it carries the signal from the other tunnel. So if this says halt, then this halt signal will be transmitted faithfully to the input of this guy. So that means when we get a halt signal, we're not going to get anything out of our clock, because remember, both inputs to the end have to be high for the output to be high. And yeah. Okay. What else? 2-to-1 selector. I think we're ready. Okay, so now let's put this together. We're trying to make this a 16-bit adder. And I've shown you sort of the beginning of what this might look like with Logisim. But there are some gaps that need to be filled in. You'll notice I didn't complete the connections for the adder and the multiplexer and the accumulator. I'd like you to do that part. But I want to show you how to make these things. So we have the instruction decoder. We've got our selectable inverter. Let's add 2 of the RAM arrays. So that's under memory. So you have 8 address bit and an 8 data bit width. So if I have an address bit of 8 that's 8 wide, 8 bits wide, that means I can address 2 to the 8th or 64,000 different inputs. And I need 2 of these. I need one that looks like the code and one for the data. And you can label these by using the text tool. We have an adder, and that's under arithmetic. So I select 8 data bits again, and I'll put that here. And what else? Multiplexer, under plexers. So looks like I've got it facing south in that picture. Let's do that. So this has a bunch of inputs, and the input 0 and input 1, that's not too hard to understand. This one doesn't tell you what it does, and this doesn't tell you what it does. That tells you it's the output. So there's a question mark, right? We don't know what these inputs are. So let's use the help file and see if we can figure it out. The file looks like this. I want the plexers library, multiplexer. So this tells you basically what the pinout is. And it says along the south edge, you've got this little gray circle and the blue dot. The south edge left side indicated by a gray circle tells us which input to route to. So on the right side, if it's 0, it selects this guy, and if it's 1, it selects that. And then the right hand side, south edge right side, is an enable. When 0, the multiplexer's outputs floating. So maybe just to be safe, we should set that equal to 1. And one way to do that is to use the constant and say that we want the value to be 1. This 0x is a way of saying hexadecimal. So here's 1. Alright, we've enabled the enable. And I want the load signal going into the multiplexer inverted. So I need another, what is it, subtract, add, store, load. Okay, so I've got inverted load going into multiplexer. I've got that part done. Store flag is going to go into the clock. I'll do that in a minute. Oh, this. So now we need the counter, and the counter is where is that again? Plexers, I thought. Here it is, under memory. So put that here. And looks like the output is going to go to both our RAM arrays. So clock goes here. What else? Accumulator. So where's that? That's under memory also, so that's called register. And it's going to be down here somewhere. Make sure that you have 8 bits selected. We're going to use the rising edge for a trigger. And I think that's everything. Gotta have something coming out of subtract. Is this subtract? Yeah. My subtract is going to be the input to my selectable inverter, so I need another tunnel here. Oh, you know what? You don't even need a tunnel. You can just wire it directly. Okay. I think I put this all on the wrong RAM array. I'd like to try this out because we have our instruction decoder is actually working for halt is working and load and store are working. So let's see if we can get that working on our main. So the way to change this memory address is use the poke tool and then use your keypad to change the value of these bits. So we know 10 is load. We know FF is halt, so you see how load is lit because it's lime green. And if I change this to FF, now halt is lit. So that looks like it's working. Subtract, I don't have that hooked up yet, but that would be 20. Alright. I think that's all. No. Okay, the other thing I wanted to mention was you can modify these by typing things directly into the keyboard like this, or you can right click and say edit contents, and when this window will open. And when we're writing our machine language programs, you'll find this is a much more convenient way to modify the result, to modify the contents of your code RAM. And when you're done, you save it as a circ file. As a circ. Shoot, I can't remember if it's called a circ or dat file or something else, but maybe even a RAM file. These are the files I want you to load on the lab, and I think that's all that I'd like to talk about for the lab. Good luck finishing that, and please don't hesitate to call me if you have any questions.